I am Dr. Rashid Ahmed from the Department of Physics of Kohat University of Science and Technology in the subject of Quantum Mechanics 1 with the course code PHY 212. We are at the lecture number 25 and the topic is uncertainty and commutation relations. In quantum mechanics, when two observables cannot be measured with 100% accuracy simultaneously, we say that they are uncertain. And when two observables can be measured with 100% accuracy simultaneously, we say that they are certain. To uncertain observables, they follow the commutation relations not equal to 0. That is, they do not commute and their commutation relations are not equal to 0, and that's why they are uncertain. On the other hand, the observables which are certain, the corresponding operators actually commute and we say that they are compatible. In previous lectures, we have developed that there is a relationship between uncertainty principle and commutation relations, and actually this is the one of the fundamental relations in quantum mechanics. But that was done somehow on the mathematical side. In today's lecture, we will see physically how two observables which are uncertain related to the commutation relations. So let's start with the idea of simultaneous eigenfunctions. So if we have two operators A and B, and A is acting on some wave function and it is an eigenfunction to it, and let's say B is another operator which also acts on this same state function or eigenfunction, and it is also an eigenfunction of it, we say that it is a simultaneous eigenfunction for A and B. If this is so, for example, in case of the free particle, the operators P and H. P is a momentum operator corresponding to the observable momentum, and H is a Hamiltonian operator corresponding to the energy observable. They commute, that is, they are compatible. So they are compatible, they are commute, and hence they have simultaneous eigenfunctions. So this is a new rule coming up, that we say that when two operators are commuting, in other words, when P and H, their operators we calculate commutator, that is equal to 0. When this is so, they commute, then they must have a simultaneous eigenfunction. So this is a new rule. And when there will be P and or another operators which do not commute, that is their commutation relation, for example A and B, another set, we will find out that there are certain physical observables for where their operator do not commute, not equal to 0, then they will not have simultaneous eigenfunctions. And by this way we will relate them to uncertainty, that when we have simultaneous eigenfunctions there will be no uncertainty, and when we will not have simultaneous eigenfunctions, there will be uncertainty. So let's say this is the eigenfunction which is simultaneous to P and H both. So this is the eigenfunction of P and H both, and you can check this very easily because P operator, this P operator is I H bar del by del x, and H operator is actually square of it. So if you apply this P operator to here, so it will differentiate this exponential function, giving you exponential function back, and k coming as eigenvalue. Normalization constant can be determined, and this is P square, which means acting 2 times. Del x acting 1 time gave you k, and del x acting another time gave you k square. So we see with the different eigenvalues, this wave function is not only the eigenfunction of P, but it is also eigenfunction of H. So therefore it is a simultaneous eigenfunction for both operator P and H. And why is this simultaneous for them? Because they commute. Over here you can see if they both commute, that's why it is simultaneous eigenfunction for P and H. Let's so what does this mean physically? So it means that when we have simultaneous eigenfunction, and in this state it is certain that measurement of momentum will give us h bar k. It is certain it will give us h bar k. And if we measure the energy in this same state, then it is certain that it will give us h bar square k square by 2m. So these two values are certainly are certain and simultaneous. So we can find out simultaneously because they were compatible. So if two operators are compatible, then they have simultaneous eigenfunction, and then we can have with certainty their values h bar k and h bar square k square by 2m. And we will see in this lecture that when this is not the case, when the two operators do not commute, they will not have simultaneous eigenfunctions, and they will not, it will not be possible to with 100% accuracy measure their eigenvalues. So there will be uncertainty between them. So simultaneous measurements for the operators h and p, since h and p are compatible. So in this slide I give you the complete recipe for the uncertainty and commutation relations and simultaneity of eigenfunctions. So if you have two operators, for example a Hamiltonian for energy and p for the momentum, and they are compatible, then by compatibility we mean that they commute, that is their commutator is 0. Then quantum mechanics allows p and e to be simultaneously measured. So this is the recipe or rule when we say that we can make a simultaneous measurements because h and p commute, then quantum mechanics is actually allowing us to measure p and e to be simultaneously measured, and there is no uncertainty between them. Now go to the converse example. We go to the converse example, and there we take two another operators. One of them is a position operator x, and another one is a position operator p. And now we know that they do not commute. That is, the commutator of x and p is not equal to 0. They do not commute. So therefore they will not have simultaneous eigenfunctions. And when they will not have simultaneous eigenfunctions, eigenfunction, then what will happen? Then when this x will act on a certain function, it will change it, and this will not be an eigenfunction of p, because they do not commute, they do not have simultaneous eigenfunction. So in this new function we will not be able to measure p. And also the other way around, when p acts on some function and gives us some eigenvalue, and it leaves that system in that eigenfunction, which is not eigenfunction of x, and when we act on x on that function we will not get any value, and it will be infinitely uncertain. Okay, so we have operators x and p, and they are not compatible, as we know that their commutator, as I have written here, then their operator is not equal to 0, they are not compatible, so they do not commute. It means that quantum mechanics does not allow p and e to be simultaneously measured. So quantum mechanics does not allow us to measure p and e simultaneously and with 100% accuracy. And this is another set of recipe where we have seen that two non-compatible operators cannot, their observables cannot be measured with 100% accuracy simultaneously. So why this is so? Because there is no state in which x and p measurements gave us definite values. And let's do an example for this statement, where we will see that x and p, there is no state. We will make sure that we will prove that there is no state when where x and p measurements gave us definite values, because they do not commute. So take an example. Let's say we have an eigenfunction. This is the eigenfunction for the position operator. So we act with the position operator, let's say, on this eigenfunction, and it gives us, this is a Dirac delta function, which is the eigenfunction of the position operator. It gives us eigenvalue, let's say, call it x prime. Now we note that x measurement finds x prime with 100% accuracy. And the rule of the quantum mechanics is that after the measurement, or after this operator acting on this state, it will leave the system in this state. It will leave it there. So it will leave the system in this state, in the eigenstate of x hat. Now this is the eigen state of the x operator, but this is not the this is not eigenstate for the momentum operator. The if you go for the now momentum operator, which is, as I have already mentioned, is iota h bar del by del x, this is not eigenfunction for it. So when you act on it, you will see that you will not, it is an infinitely uncertain. So P measurement is infinitely uncertain. On the other hand, if X and P would have commuted, then this state would have also be the simultaneous state of P, and we would have find that the that two operators are simultaneously measurable, as was the case in momentum and energy. But in this case, position and momentum, there is no simultaneous eigenfunction, and when you first measure the position, this is not the eigenfunction of momentum, and when you act with the momentum on this, you will not get any value, and it is infinitely uncertain. So this was the somehow the message of today's lecture, where we would wanted to establish a relation, physical relationship between commutation relations and uncertainty principle. And we have seen, because of the commutation relations, when they are not compatible, there are no simultaneous eigenfunctions, and then we have uncertainty. So to make it concrete, we see that uncertainty for energy and momentum, when we have energy and momentum, then the delta E, that is the uncertainty and the energy, and the delta P, which is the uncertainty and momentum, their product is 0. That is, delta E multiplied by delta P is equal to 0. That is, they are certain, they are compatible, they are certain. But on the other hand, if we go for position and momentum, we see that the this relation, that is the delta X, that is the uncertainty or the change in the position, and the change in the momentum is not 0. It is must be greater than or equal to h bar, or this is not equal to 0, which means that there is uncertainty in the position and momentum. We call them conjugate variables, and they are non-conjugate. Whenever delta X and delta P come together simultaneously, there will be uncertainty. So compatibility operators, so suppose that two observables have corresponding operators A and B, and they are not compatible. Then when they are not compatible, let's call their commutation relation equal to C, then this will not be equal to 0. So when the two operators are not compatible, they are not simultaneously determinable, then A and B, they have C hat as their you can call this commutator as C hat. This is not equal to 0. We now do some statistical analysis for this as well, and we say that measurements of A and B are uncertain by amounts delta A and delta B. So there are two operators, operator A and operator B, and the uncertainty operator A is delta A. This is uncertain by amount measurement in A of amount delta A, and B is delta B. And when we multiply this delta and delta B, this must be greater than or equal to the expectation value of C. And what is the expectation value of C? This is the commutator, the A and B, whatever the commutator is. But this commutator, this must be greater than the expectation value of the C. And what is expectation value? It is actually calculated from the root square mean deviation. Root square mean deviation is calculated in this way. If you have A, some observable, and you make many replicas for the system and measure A, and every ensemble, in this ensemble, every replica is giving you some value, and what you can do, that you can take the average and calculate this equation, and we call it a root square mean deviation, and this is actually the expectation value. This expectation value of any observable is determined by this formula. We have already learned this formula, and the expectation value for any observable or is I mean the same formula, where you can see that for value for the psi in here with A minus A hat, and A minus A hat acting on the psi and on the ket and on the broad together. So this is the same formula as there or there. So you combine these two formulas and you get the expectation value in terms of root square mean deviation. So we have found a very fundamental relation between commutator and uncertainty, and we have seen that whenever two operators do not commute, they are not compatible. They will not have simultaneous eigenfunctions, and that's why they are uncertain. On the other hand, if two operators commute, that is, they are compatible, they will have simultaneous eigenfunctions, and there will be no uncertainty. So that's a very fundamental relation in quantum mechanics between commutator and uncertainty. So commutator relations and uncertainty principle are related to each other. Another related concept is a complete set of commuting observables, and I will show you that by the complete set of commuting observables you can actually remove the degeneracy from the from one of the observables. Let's say H is an energy operator, and it has degenerate eigenstates, as we have seen in the previous lectures, that when H has degenerate eigenstate, it means that it has many eigenstates which give you same eigenvalue, and it can be removed with the help of measuring P. Since P and H commute, we know that H is degenerate and P commute with it. We can use P to remove the degeneracy from H. I repeat, if H is degenerate, it means it has many states from which it gives its eigenvalue, and it commutes with a P. Then we can use this P operator to remove the degeneracy from H. So how we do this? Consider this is the recipe for removing the degeneracy with the commuting observable. Consider an operator A has a degenerate eigenvalue A. Okay. So consider another operator B that is compatible with A. Okay, so operator A is degenerate, having a degenerate eigenvalue A, and B is compatible with it, but non-degenerate. So this phi AB is actually, so we will have another set over here. So this will be the eigenvalue of phi A, but this is the eigenvalue of phi B. So you see that this is non-degenerate, this is non-degenerate, and this is degenerate. As we have already learned that the degenerate eigenvalues are less, the non-degenerate eigenvalues are less than the degenerate eigenvalues. So since operator A is a bigger one, it has a degenerate eigenvalues, but since it is compatible with this, it has simultaneous eigenvalues with B over here. So this set is reduced, and degeneracy, this from here is actually removed with the help of this compatibility with B. So we knew that this is for B and A is the bigger circle, but because of the compatibility we could reduce, and we see that these are the wave functions which are compatible with the A, and this is a lower set. Even we can resolve it further, and we can come over here. If we have another operator, let's say operator C, and operator C is also compatible with the operator A, and we can have over here phi A B C, and it is even the lesser rate. So more we resolve, the more quantum numbers we need, or more eigenvalues we need. So it up to the eigenstates, if it are there is a lot of degeneracy. So you come, for example, you come from phi A B C to you come phi A B, and then you phi A. So you remove the degeneracy by this way, that you check the compatibility, and non-degenerate eigenfunctions are less set and lesser set, and so on. So in this way we use commuting observables to remove the degeneracy. Like over here you can see that this phi ABC is a wave function of A, is also an eigenfunction of A, eigenfunction of B, and this simultaneous eigenfunctions. But by completely measuring these three observables, these three eigenvalues, we can remove, we can resolve the state. For example, the bigger circle phi A, then the bigger circle phi B, and then the phi A, and so on. So you can come down there, and by removing, by using the commuting variables, one can remove the degeneracy in the operators. And another concept is maximally informative states. What does this mean? Consider these are called good quantum numbers. So we consider we have 5 operators A, B, C, D, and F, and also assume that first 3 of them, that is A, B, C, are compatible with each other, and the last 2, that is D and F, are compatible with each other. So since they are compatible, we know that they will give us the complete information about the state. So it is informative, maximally informative, and this will also give us the complete state information about the system. So this will also is a maximally informative set. So we have 2 sets of operators which are compatible among themselves, and they give us complete information about the system because they are compatible, and we can resolve down to one state. and but they are mutually not compatible. This is not compatible with this. So this is okay, because these two states will generate a similar kind of information. So this is maximally informative, and this is also maximally informative. So we have seen that the maximal information it comes from the commuting operators, and there could be more than one sets where commutation is possible. So in today's lecture, what we have seen that we have developed the uncertainty and commutation relations on the physical grounds, and we have seen that when two operators are compatible in mathematical sense, we have done this before, and if they are compatible, then they will have simultaneous eigenfunctions and eigenfunction or functions, and then they can have simultaneous eigenvalues, no uncertainty. And same is not the case for when they are not compatible. And we can also remove the degeneracy from the system with the help of commuting observables, commuting variables, and we can also have a maximally informative set of commuting operators, because this will give us something which are compatible, and we will get complete information about the system. With this, I thank you all.